suggested we call it Zentropy. So that's where the name comes from. So it started in June 2021, about close to 3.5 years, or close to 4 years now. All right. So let's talk about what this Zentropy is about. Again, my name is Ziquelio. I'm a professor at Penn State. Has been here now for since 1999. So Zentropy is basically Z plus entropy. And we all know Z very well. It's a German word, Zustandssumme. It's used for partition function. So the idea is really that this is what we typically have, the partition function. And so the partition function of a system is a summation of the partition function of different configurations. The only change we made is that instead of total energy, we use free energy. In the MVT ensemble, canonical ensemble, we have used Helmholtz energy. So that's really the major difference, or the only difference, actually. The question, of course, is that how do you get the configurations and how do you calculate the FK? Of course, the reason is also why we use FK instead of EK or UK in the typical case. Okay, so let's go back and see one step back, say, what is entropy? Okay, I visited Vienna, this cemetery in 2014, and I took the time to visit Bosman's stone graveyard here. As you can see that there is S equal to K log W. That's all we teach our students, and they say, okay, entropy is equal to KB log W. The W is number of configurations. And what is important, because that's basically our second law. Right? Second law says that any process, any internal process, we often say it's irreversible. It turned out that all the processes are irreversible if it happens in the reality. So it's going to result, any process, it can result in entropy production. Sometimes we say it's the isolated system and so forth, but you can always define the internal process as a system. You can study. So I would just say any process, anything happens, it increases entropy. Okay. So how do we measure entropy or calculate entropy? We know that if we can measure heat capacity, that's heat capacity Cp is the heat capacity on a constant pressure. As we usually do the measurement, we integration from 0 Kelvin to temperature. To a given temperature, we get entropy at that temperature. And in order to make that integration, we have a third law. We say, okay, entropy at 0 Kelvin equals 0. So you can do that integration. And how do we know S equal to 0 at 0 Kelvin? Well, we don't know, really, because we cannot go to 0 Kelvin. But we can do trajectory. We can see that if you go to temperature very, very low, millikelvin, we can calculate, we can measure Cp. We can also measure Cp over T. And both of them approach 0 when the temperature is close to 0. But how do we calculate it? We showed that equation from Boltzmann's gravestone. But the question, how do you get a W, right? How do you get a W? Or rather, is that equation really accurate? Okay, so then we have to go back to one step back even further. We know entropy is part of thermodynamics. So let's look at what thermodynamics we think about, right? I want to talk about 3 domains of thermodynamics. The first one is classical thermodynamics by Gibbs, and he visited Europe 150 years ago, and learned from Europe. He came back, developed the equilibrium thermodynamics, this combined law with no internal processes. That means no entropy production. And then he realized that he must get entropy, not just a change of entropy, because if you want to calculate the change of entropy between two states, you have to know the entropy of each state, and then do the difference. Then you see that's entropy change, right? That's why after 40 years, he developed the classical statistical mechanics. Now he can calculate entropy. I'm going to show some equation from him. So that's 1901. We got his paper down for the classical statistical mechanics, which was developed based on what Boltzmann, Clausius, and Maxwell had before him. And we also know that 20 years later, we got quantum mechanics. That's Schrödinger equation. But Schrödinger equation was not solvable until also the statistical mechanics now is changed to quantum statistical mechanics in 1930s. But until 1960s, we now get a density functional theory. Now we can calculate. We can solve the Schrödinger equation, and we can do quantitative prediction. We can calculate FK. That means for a given configuration, that the statistical mechanics will have configurations, right? So for any given configuration, we can calculate the free energy. Okay. So that's the revolutionary. Of course, as 1960s, we get a theory. The really explosive calculations started in 1990s, another 30 years. When we got this density functional theory, we got the LDA, GGA, and this kind of things. And however, there's another direction which happening in parallel. It's the non-equilibrium thermodynamics, which we call it irreversible thermodynamics, which was a key contributions from Onsager and Prigogine in 1930s and 50s. They capture flux or change in the system of some variables. And I would argue that cathode modeling in the 1970s, when it's kind of named, it's actually doing the thermodynamic modeling of non-equilibrium systems, because we have to define the energy of non-equilibrium state. Okay, we have to have the unstable state, for example, chromium FCC. Okay, and I really think that I benefit a lot from Max Hillard, that he put this entropy reduction into the free energy function, into the combined law, because you see, when Gibbs did it, he put it 0, right? But it's not equal to 0. So actually, I should put it larger equal 0. However, the 3 domains of science have been studied in the last 150 years. They're kind of separated, right? We talk about equilibrium thermodynamics, we talk about quantum mechanics, we talk about the non-equilibrium thermodynamics. They're not just separated, but they're all thermodynamics, right? So how to put them together, which I think is that Zentropy does that. Zentropy put all 3 things together, and it creates a free energy landscape. So you can talk about the basins and the maximum and the saddle point, everything on this energy landscape. I showed you some of the papers are here, and this, I think it started from maybe 2009. We got this systematic understanding all the way until this year. Okay, so let's think about how we connect these experiments into the into the theory, right, together. So we know that we do experiments, we observe things, then we develop phenomenological correlations, we develop models. That's how we got the first law, second law, third law, and the Newton's law, everything we have, right? So then we go to fundamental, and then you have to simulate the experiments with the simulation. We create the new models, we do the calculations, we do simulations. Okay, the question I have been asking myself in the last 25 years since I came to Penn State, or before that as a grad student, is that can we do something direct from fundamental laws to the observation? Okay, because we know that every model we create is an approximation. It does not capture the full reality. Okay, that means if the model doesn't do that, of course, simulation calculation will not do that either, right? That means it's always a part of the picture. Okay, so let's go back to quantum mechanics. Because quantum mechanics is really fundamental because it predicts things we do not know to start with. Okay, we have the Schrödinger equation is about the electrons and nuclei, and there's interaction of them. Then DFT can solve them. Okay. However, DFT has one limitation. Is that it talks about the ground state configuration. That means at 0 Kelvin, of course, again, we cannot go to 0 Kelvin, but you can calculate it. It says at 0 Kelvin, there's a ground state. That's the lowest energy. That lowest energy configuration or state is defined by unique electron density. at equal to 0 Kelvin. Of course, now we know that we can go to high temperature for that configuration. We can do perturbation. We can see how the electrons redistribute themselves using the Fermi-Dirac statistics. We can calculate the entropy of electrons. We can also calculate the phonons, right? So if we put the phonons and electrons together, we get the quantum entropy of that configuration. Okay, so I call it the quantum entropy. Now I have two contributions for a given configuration. Particularly here is quantum state configuration. We calculate the thermal electronic contribution and the phonon contribution. We get the entropy of the ground state. We know the energy, right? We can calculate energy. We can calculate the phonons, the electrons, so we get the free energy of a configuration. Okay, so that's very nice, right? So we can predict the free energy. You know, from thermodynamics, we know that if we can predict the free energy, we should predict everything, right? Because free energy is the total energy of a system, and then we should predict all the properties. However, what happens is that we do a lot of calculations, or everybody did a lot of calculations too. We found that there's lack of quantitative agreement with experiments. Okay, that means in this kind of theory, we're still missing something, right? So every time we have to refine the model parameters by experiment data. Now it's a truth, we have a model by model parameters, right? And then our prediction doesn't agree with the experiment fully, quantitatively. Okay, that means we're missing something. The question is really that we started asking this question about in around 2002. That's when we really get a lot of DFT calculations. We find that even we take all these phonons, FK, calculate the range of a configuration, we still cannot fully match the experiment. Of course, there are some larger issues here. Sometimes it's just completely off, way far away from experiments. So we try to figure out what the issue here. Okay, I want to show you a graph here, which is from John Purdue. If you do DFT, you know John Purdue is a person and his team created this GGA for the DFT calculation, enabled DFT calculations for accurate results. But he showed this diagram in 2021, shows that elephant. We all know the blind people, and elephant, and you always have limited on your observation. So that's why that's related to when they developed the scan potential method GGA in I think it started 2015 until today, still improving. So the case that it means everything we're doing is only part of the whole complexity. So how can we put them together? So we can have the full description of the whole elephant, right, so to speak. Okay, let's go back to the thermodynamics now again. So when we talk about thermodynamics, we always, let's get here. Okay, we talk about a system. We have to study a system. And then we talk about the surroundings. Then we talk about the exchange between the system and the surroundings, right? So we have three types of exchanges we do. We change energy, heat. So first we change heat. And then we exchange work, we change mass. So these three are independent. We can independently change heat, independently change work, and independently change mass. Okay. So for every mass, it has energy. Each component we call it UI. It's the partial internal energy of that component. Then we got the total energy added to the system, where it be you have the heat, work, and the mass, add them together. Then you get the first law, say this has to increase the internal energy of the system. Okay. And then we have to think about entropy, right? Because we talk about entropy is important, that's why I think about entropy. So heat addition has entropy. That's Clausius entropy, dq over T. And then each component has entropy, the partial entropy of component I. The work does not directly increase entropy, but the work affects what's happening inside the system. Okay. So now put together, you get a total entropy change in the system. You have the heat, you have the mass, and the internal process. Okay. So three together change the entropy of the system. Now the interesting is that these two are the exchange between the system and its surroundings, but this one's inside the system. So this equation is extremely important because it connects outside with inside. Okay, now what's the internal process system? Well, remember that we disturb the system, by heat, by work, by mass. And then the system can do something, right? And we learned from the long time ago, Le Chatelier said we have Le Chatelier principles. That means if you disturb the system can do something to undo partially what you disturbed. So that's got then through the internal processes. Okay, so that process will produce entropy production. That's based on second law of thermodynamics. So that means now we can put them together. Now, however, we know that they're violation of the Le Chatelier principle. As you see, this is 30 years ago now. So when I was in Sweden, I looked at this one. I thought, gee, so why there's a violation of Le Chatelier principle? Okay, we know that the example is you have this ammonia reaction. So if you add the nitrogen, right, the Le Chatelier principle say, oh, somebody has somebody can mute some noise from people there. Let's see if I can mute them. Okay. I just muted the one participant, so that's making noise. Okay, all right. So that means if you add more nitrogen, the reaction should reduce this addition, right? If you remove some nitrogen, the system should produce more nitrogen. That's called the Le Chatelier principle. Okay, so that means what happens is that if this is the kind of N2, the molecule, and this is the kind of change ratio of it, right? So what it means is that if you start from this point, if you add nitrogen, the system will go back. If you remove nitrogen, system will increase it. So it's good. So that's our base Le Chatelier principle. However, if you add more nitrogen to this region, and then the system will go away from that point, you will produce more nitrogen. Okay. So that is called the violation of Le Chatelier principle. If you find any chemical engineering book, textbooks, talk about this violation. However, this is really not a violation. Why? Because if you change from here to there, you add too much of it. Okay, you actually reach a new equilibrium. Of course, the question is that if you sit at this point, if you add more, you don't produce more, right? Because at this point, the system is not stable. You disturb it, you will go to either this equilibrium, go to that equilibrium. You never stay there. Okay, so that new equilibrium stay. So because you depends on your system, so we have to be able to understand the system and predict it. Then we need the free energy. Okay, that's what I learned from Hillard. I call the Hillard line equilibrium thermodynamics. You get this equation. Okay, you calculate the entropy work and the chemical potential and the internal process. Okay, the important thing is that you have these conjugated variables. Okay, so x are the potentials, y the potentials, x the molar quantities, and the internal process has the same thing. You have the driving force, you have the process that will happen together. The most challenging quantity is the entropy. Okay. It's complex because remember, I have three terms. You have internal entropy reduction, and you have heat, you have mass. So how do you calculate the entropy? As I mentioned before, Gibbs realized that the problem because he realized he could not calculate it, right? He could not calculate from the Boltzmann equation. Okay, that's why in 1901 he developed the statistical mechanics. Okay, he said he imagined that the system consists of different configurations, all possible configurations. Okay, so the system actually experienced all of them and put them together. And that was later called Shannon information entropy. So in this equation, partition function of a system is a partition function of a summation of each configuration. Each configuration has total energy Ek. If you solve this equation, you get the probability of probability each configuration, you get entropy. So this entropy is different from what Boltzmann had, right? Okay. Then you calculate probability. Probability is equal to Zk over Z, each configuration. Okay, so how does it connect the Boltzmann entropy? If each pk is the same, that means you have 1 over W, but it's identical. And then you get Boltzmann entropy. So what does it mean? That means Boltzmann entropy is an ideal case. When all configurations have the same probability. If the same probability, that means have the same energy, right? But of course, we know that from the DFT, no, it's not. That's not the case. We have the ground state has lowest energy. Other states, other configurations have a highest energy. So it has a probability. So now that means we can solve this one, right? Solve this one. Okay, so that's what we have. So in your system, you have many configurations, and the entropy of the amount of configuration is pk log pk. So that gives kind of Shannon information entropy. So this partition function. So that works very nice. That's how we teach statistical mechanics. I call it top-down view because you look at the system, you decompose it into configurations, you say, that's good situation, okay? However, if each configuration also has entropy, so that entropy is not showing up in that entropy by Gibbs, right? Statistics. So this entropy, as you mentioned, we can predict from quantum mechanics by DFT. So that's from bottom up. From 0 Kelvin, we go to high temperature with different configurations. We have different probability, different entropy, right? So that means those entropies they have to be added into the total entropy of the system. That means we have two terms now, right? I call this information entropy. This will be quantum entropy. So I have to put the two entropy together to describe the total entropy of the system. So that's our theory. We started working on this one. We didn't do this exactly in 2008 when we started this problem, solve this problem. Instead we started with the partition function. We started with this one. Okay, so this is the outcome of it. Okay, so that was called in 2021 called Zentropy. So Zentropy basically combines or integrates quantum mechanics and statistical mechanics. I call it classical statistical mechanics. So that is in that way we can get the all entropy correct, and then we can compare with experimental entropy, which can measure. So it's also another very important thing we realize that when we do this kind of summation here, right? Each configuration must have the exactly same external condition. That was exactly what Gibbs mentioned. That means each configuration must be the same nature. Only difference is configuration. Okay, so that means when we put this in together, for example, if you take the canonical ensemble, that all configurations must have the same NVT. What does it mean? That means when put them together, we actually create a homogeneous system, right? And because every configuration has the same kind of nature. Same N, same V, same T. So only difference is internal configurations. That means we talk about a homogeneous system. However, homogeneous system could be stable, could be metastable, could be unstable. So then we do the minimization of the free energy to figure out whether the system is stable, metastable, or unstable, or we do derivatives, right? We calculate the second derivative, we calculate the first derivative, we compare, see what's stable or not, okay? So that means that this approach really predicts the landscape. Okay, that means the free energy has function of variables, right? You can control N, for example. You control V. You control T. Okay, so you can change it. Then you get an energy landscape. This landscape will have basins, for example. Again, this is the diagram drawn by publisher of my newest book. You can in the basins. You can get the saddle points, there's saddle points. You could have the apexes, the maximum, okay? Then you have the barriers. So it's key is the barriers. Now, if you get a free barrier, you can calculate the kinetic properties. That's what we're working on now. We just realized that not too long time ago. But it is very important concept. You can calculate the entropy of unstable states. Right? For example, if you take this point, maximum point, you do derivative as function of temperature. Suppose this temperature. You can actually calculate entropy of unstable state. But we often tell ourselves or teach our students that we cannot calculate entropy of unstable states because it's imaginary frequency. However, that concept is on the static of atoms. Assume atom doesn't move at the beginning, but atoms are moving all the time. So we're starting with the wrong assumption to talk about the stability. All right. So the first case we started with 2008, as you can see, 2008, 2009, is about a cerium. Cerium is a very interesting element. It's used in magnesium alloys. It has a ground state. it has some high temperature state, and then have a critical point. Okay. And of course, between the non-magnetic and ferromagnetic, you have anti-ferromagnetic. Okay. So we put them together. We first take two configurations, then we take three configurations. They show three configurations. So you have this energy as a function of volume. So this ground state has low energy and zero pressure. And this is the high temperature configuration. It's a ferromagnetic, has high energy at 0 Kelvin. And this is the one in the middle. Okay. Now, if you calculate this is 0 Kelvin, we can calculate the energy of them. We can mix them, right? So now 0 Kelvin, well, this is a tangent. But if you increase temperature, you get extra entropy here. So extra entropy, this is the information entropy, Gibbs entropy. When temperature increases, this information entropy becomes more and more important. And to some temperature, there's no barrier anymore. When there's no barrier, that means you get a critical point. And now you can see that the energy barrier between two states at 0 Kelvin and the 100 Kelvin, you see the barrier change. And then at a higher temperature, barrier become smaller and smaller and becomes 0. So we can predict the transition temperature. Now we can predict the TP diagram now. So this is at 0 pressure. And then when pressure increases, right, temperature increases, you get a critical point. So then the two phases, right, they're still both FCC, but different magnetic states, they become one phase. So again, there's no model here, right? No model. It's completely predicted from the 0 Kelvin energy and the free energy of three configurations and the simple size experiments. Now, of course, in the experiments, we measure pressure, volume. Okay. Now we can change the pressure to volume. We got a temperature volume phase diagram. And they can see that, okay, now you get a miscibility gap. You get two-phase separation. You get a miscibility gap. This is a low pressure, low volume phase. This is a high volume phase. Okay. Then this miscibility gap will shrink. And at a certain point, it becomes merge together. So these are the isobaric line, the fixed pressure. This is ambient pressure, and these are the different pressures. Okay, and the symbols here for experiment, the experiment data, volume as a function of temperature at a given pressure. So here, more important is that we can see that at a critical point, we have divergency. So some expansion V to T is divergent positively to infinite. That is the critical point. So we are pretty happy. Then we look at another problem the next year. It's about a negative sum expansion. We know that there are materials with negative sum expansion. One of them is INVA, was discovered in 1897. So this iron-free platinum is not exactly INVA, but it's one type of INVA. We take this one because it's a simpler calculation because PT is non-magnetic. In the original INVA was iron and nickel, so it's more complex. So here we shows linear sum expansion as a function of temperature. At 0 Kelvin is 0. And temperature increase, some expansion, increase, become positive, then started to decrease, then become negative, and then become positive, and then keep on positive, right? So you get a volume will shrink in some temperature range between here and there. So then we do the same approach. We say now we have iron-free platinum. Iron is magnetic, so we do the spin up and spin down. So we have 9 iron atoms. We have 512 spin configuration. Because of symmetry, 37 of them are unique. So we can calculate all of them. Okay, the spin configuration. We calculate all the energy at 0 Kelvin. Then we calculate free energy. Use DFT. Then we mix them. Now we find that even though the ground state is stable in terms of its lowest free energy at all temperature, however, we have many other configurations. They have a probability to increase at a certain temperature. Okay, and even though it's stable at a very high temperature, this one lowest energy, but the probability decreases very rapidly. Okay. So now we can predict all the properties now too, because all the properties are derivatives of energy. We can find that the Barker modulus decreases dramatically. That's what people say. You get this kind of softening, right? They call it phonon softening. But here it's not actually no phonon softening at all. Just competition of the different configurations. It's almost negative Barker modulus. And then can I phase diagram too? Okay, with the TP diagram. we can change, again, the symbols are experiments, and the lines are the prediction. Then we can go to the TV diagram. Now we see it's different now, right? Previously, the curve goes all the way up, but now it comes up and then goes back. The volume is decreasing in this purple region when temperature increases. The reason is because the smaller volume configurations are become more and more popular. Even though all of them have a positive thermal expansion, all of them, but when they put it together, the total volume should decrease. Because the smaller volume configuration are replacing the larger volume configuration, the ground state. All right, so it turns out you have a negative thermal expansion, then you have negative thermal expansion divergency. So something becomes next to infinity as a critical point. So that's it. So the line here is experiment, prediction, and the symbols are experiments. Again, that's 2010. So since then, we have doing some other works. For example, this is 10 years later, 2022, we calculated the E-string equivalent called strongly correlated physics with, turns out it can predict very well with our model. Not our model, our theory, because we don't have a model. We take the quantum mechanics and put in the statistical mechanics together. And we can also calculate short range order range too, okay? Because we can look at the neighboring and different configurations. The latest work we had was very amazing is with Professor Chi-Jun Hong for Arizona State University. Now, we knew each other for a long time because his advisor was my good friend, Axel van der Waal at Brown University. We interacted over 25 years now almost. So I talked with him to 2023, because he works on liquid. I said, maybe we should predict the entropy of liquid. We know liquid is very hard, right? And Chi-Jun was very smart. He figured out in less than 2 months, okay? So now we can calculate the entropy of liquid very accurately. Use MD and Zentropy. So what it means is that so how to calculate the entropy configuration of the liquid, that's pretty hard. But he figured out we can use this radial distribution. So the blue one here is for aluminum. Blue one is FCC, okay? FCC is mostly, 12, right? Coordination number is 12, okay? But if you go to liquid, it's different now. In liquid, the coordination number has distribution. As soon as it has a distribution, you can calculate entropy. That's a probability, right? PK log PK. So it turned out for aluminum liquid, he calculated the entropy of configuration, information entropy, is 6.3. Remember, we have two entropy. We have the quantum entropy, we have the information entropy. So what is the quantum entropy then? Well, we can calculate too. Turns out the quantum entropy of the liquid is around over 60, right? So this is very small, only 10%. The red one is only 10%. The electronic one is a little bit, it's even smaller, right? So it's not a big deal. However, it's a big deal if you calculate transition, the melting temperature. Because melting temperature is a delta S, right? It's a delta S. So that means delta S will be different dramatically without this one. Because delta S is between liquid and solid, right? You see, liquid and solid difference, delta S, is less than the S configuration. So S configuration is more than 50% of the total S. That means your temperature at least a factor of 2. That's why all the MD simulations predict a very, very high melting temperature, because the delta S was incorrect, at least by half, if not more. So then he made one step further to calculate melting temperature. He also calculated this delta S, the S configuration contribution is between 50 to 70% of the delta S. So it's huge effect. Now, with MD, you can now very accurately predict the melting temperature now. So it's very, very innovative approach by Chi-Jun. All right, so we also work on superconductor. We talk about the charge density difference. The idea is that we thought maybe we can also apply DFT to superconductors. Of course, people say you cannot. Why you cannot? Because superconductor is about the Cooper pairs, right? You need 2 electrons at least. But the density function is 1 electron. But however, both of them are reflected by the charge density. Remember, that's the foundation of the DFT, is the electron density. So then we thought maybe we can do that. So we get a project from DOE. We said, let's compare the configurations. We see one is superconducting, okay? Another is normal conductor, right? So we did. So we take aluminum as the example first. Turned out, if we do the difference, if we perturbate the FCC aluminum, get another superconducting configuration, we believe, we actually can find this one-dimensional electron tunnels. We think this is a 1D electron superhighway. The electron goes that way without any barrier, or it's not distracted. Okay. So of course we did aluminum, then we must do YBCO, right? High T. So we did high T too. So it's the yttrium barium copper oxygen. That's a superconductor. And what happens, you see, this is a copper oxygen layer. It's very rigid, right? Very high symmetry. But in the middle, you have this is distorted structure. Okay, just like it distorted aluminum, but this is automatically distorted because the energy will be lower. So we can also calculate what we found again this one deep tunnel too. You see, the electron, the hole, actually this is the hole, are connected in 1D. That means the hole or the electron has this pathway which can go very fast without scattering. Well, our paper is still in the archive, but we're still trying to publish. As you imagine that we get pushback from the community because they have different theory. Most people think DFT is not applicable. All right, so if we can get a free energy, we can calculate many properties now, because most of the properties are second derivatives of free energy. For example, some expansion, right? Some expansion is basically the derivative of the free energy to strain or to volume twice, okay? Or to pressure twice, or to temperature, sorry. So the very important concept is that on the diagonal direction, all the terms are between conjugate variables in the free energy function, in the combined law. So they'll always be positive. They never become negative. When they become negative, it seems to become unstable. However, all the other properties we measure, they can be both negative or positive. The reason because they are not conjugate variables. They're competition between different configurations. Okay. So we also lately we started the property between the derivatives between the two potentials. For example, between the temperature and the chemical potential. That's thermal transport. Okay. Between stress, between electric field, that's electric migration. Actually, those are properties we're talking about. For example, Seebeck coefficient. What is Seebeck coefficient? Seebeck coefficient is related to the chemical potential electron to temperature gradient. Okay, so it's not kinetic coefficient at all. It's really the thermodynamic properties. Of course, thermodynamics, we'll talk about the non-equilibrium thermodynamics too. All right, so I wanted to close my talk. That we have I had a paper last year on the topic review at the Journal of Physics Condensed Matter, which kind of summarizes our theories. And then it's predictive because it doesn't need any model. It doesn't need any feeding parameters. It's from the DFT and the statistical mechanics. And it covers three topics: equilibrium thermodynamics, non-equilibrium thermodynamics, and Zentropy, and the theory of cross phenomena. Okay, the summary is that I hope you will look into the Zentropy theory. It integrates the quantum and the statistical mechanics, and it can quantitatively predict the free energy landscape. Okay. So now we're extended to predict many properties. For example, we just wrote a proposal to predict viscosity. Okay, predict the straight strain curve, because that's all in terms of energy. And it builds on the DFT-based prediction of ground state and then non-ground state configurations. Of course, they're not easy to figure out what are the non-ground state configurations. Ground state is easier because you can minimize energy, but non-ground states, you have to really look in the system, what kind of internal degrees of freedom you have. So that means there's some systems very complex, right? Like a polymer, like a biological system. Even we don't know the ground state, right? But we believe there is a ground state, okay? Then we can develop work with a mathematician to develop we call it Zentropy enhanced neural networks. That means we believe the system, doesn't matter how complex it is, has ground state based on quantum mechanics. Then any measurements we have are just a different configuration together from statistical mechanics. Okay. And so we were talking about this this approach last year or two. Then turned out that people already use this approach in AI already. These are the two papers from a group in China, and it turned out that they published papers last year already. We didn't know that. That was good, or good or bad. We thought we're going to publish our paper first. Turned out that two papers already used this one for feature selection and uncertainty quantification. And we are now developing a Zentropy enhanced neural networks, and it can hopefully digest a very complex system, start with concept of configurations. Okay, to promote thermodynamics as a very important foundation for science, I started to do this YouTube channel. I started after Thanksgiving last year to put my understanding of thermodynamics into this YouTube channel. I hope I will be able to continue to develop lectures, put on YouTube. And if any of you have some topics you want to discuss, I will be certainly interested in develop some special lectures on different topics. With that, I want to thank you for your time and attention.
Thank you. Well, it's an interesting talk. There's definitely some new perspective on thermodynamics calculation. Any questions? People want to come here and because I think probably
Can you hear from?
yeah, just that's better. So, yeah, he can feel.
Can you hear?
Yes, I can hear very well.
Thank you for your presentation, your talk. It was very interesting. I had a question. When you add the statistical contribution to and the quantum contribution to the I'm sorry, the statistical entropy and the quantum entropy, when you add those two, how do you define the ensemble?
Okay, so ensemble, we do this canonical ensemble, that's MBT. So we don't know how many configurations we're going to have, right? It depends on your size. So you fix the size of your system first. For example, we fix 12 atoms. Okay, of course, sometimes you might 12 atoms not enough, right? So you do not know that. So what we do is that we change the size. We do the calculation, see whether you converge or not. So it basically means how fast, how long the interaction is. Yeah.
So I'm asking about the quantum side of it.
Yeah.
You can't use that statistical ensemble for the quantum side.
So what you do is that, no, we do. We actually do that. So for example, in that iron 3 platinum, we have 512 configurations. So we calculate 37 are unique due to symmetry. So we calculate the energy of each configuration by DFT. So we got a 512 energy with quantum entropy.
So, okay, maybe let me rephrase it a little. How do you define the temperature for your quantum?
Okay. So that's a great question. So what temperature, if you calculate entropy, let me share the slide. So that's go back to my quantum slide. Okay, let me share the screen again. Okay, it's here. So in these two calculations, you have temperature inside. Okay, so you have two temperatures. You have temperature here. You have temperature inside of each. So for each configuration, you do 3 calculations. You calculate this one, you calculate that one, calculate this one. This one has no temperature, only have EV. These two has temperatures inside. You can reorganize them. If you want to take extract the entropy, you reorganize them like this. Because each of them have the E and the S. You reorganize them, you get a total E, you get a total S for each configuration. So that's what we call the quantum entropy.
Okay, but in that entropy, your partition function has a temperature in it.
That's right. So that's so then you go to the partition function.
Where does that come from?
Okay, so what you do is that now you have many configurations, right? You have many configurations. So they do is that you put them together like this. So each one, you calculate zk for each configuration. Then you sum them together, you get total z. Your pk is just zk divided by z. So you have sk. You calculate pk now, the given temperature. Then you can calculate total s. From total s, you get total f.
Okay, but say in your quantum mechanical entropy contribution, what is T there?
Oh, T is inside the equation. We have the equation. I can pick up any paper we have. Let me just pick one paper. The one we had, the earliest one is 2004. This one. Okay, this is our first paper about the entropy of the any configuration. We talk about ground state configuration. So what you have is that, so this is your phonon. You see, that's how you get a phonon for energy. So you get a frequency, you get T's here.
Okay, so I know where to look now. So thank you for pointing me in the right direction. I don't want to dominate the questions here.
And just go one step further. So for the electronic entropy, you have two entropy, right? Currently, you have two components, electronic and the phonon. Okay, so the phonon is here, electrons here. So F here is the oh, I didn't put it. We should have that. F is the Fermi-Dirac distribution. Has temperature there too.
Mhm.
Yeah.
Okay, all right.
Thank you.
Yeah, any,
We have Wenjuan. Wenjuan has raised the hand. Wenjuan?
yeah,
Is it my turn now or?
yeah, go ahead, go ahead.
All right. Thank you very much, Professor Liu. It's really a thought-provoking talk. And I also want to thank you. You know, we cited a lot of your papers over the past many years. So my question is really, I'm an experimentalist, and we really want to see how these type of things could help us better design materials. And one of the questions that we work on, like the no-equilibrium process that we were thinking about, is really, for example, just metal oxidation. And like now we have the quantum mechanical understanding of those things. Like, how can these tools better help us, like designing? Let's say I want to minimize oxidation rate, and I know the bulk composition is like a foreseeable pathway of using such tools. Like, what are your thoughts?
That's an excellent question. I want to show this paper by Qijun. Okay.
Okay.
It's extremely important because, for example, oxide, sometimes you talk about sublattice melting, right?
Yeah.
That sublattice kind of melt because the oxygen is so fluid.
Yeah.
But another one is not. Okay. So that's extremely important concept, I think, which I want to show this paper. Let's get this paper. I think this paper, Qijun did wonderful work. You look at the table here. Okay, this table is extremely, I think, informative in my opinion. Again, it's all his work. I just he did all the calculating in the table. So you see, zirconia is one of the very important oxide, right? Okay, zirconia has vibrational contribution at a given temperature. I forgot what temperature now. Yeah, 2800, right? You see, 76 is very big, joule per Kelvin per mole of atom. However, the configuration one is 4.4. Okay, so that's pretty big, right? You think about this one. Okay, now if you talk transition, this is the 4, delta S is 11. Okay, oh, so not here. Put the liquid, not here, right? You see, your delta S is almost exclusively your configuration entropy difference now. So that means you want to talk about any transition, any kind of emergent behavior, that one dominant. So that's what I think when we're talking properties, right? So you have to take that one into account. Otherwise, your property will be way off because it only captures the main part of, not main part. The quantum entropy is still dominant in most conditions. But your properties, which actually be controlled by that configuration entropy.
Okay.
So that's what I think material design will come into play. Because you want to get some emergent behaviors, right?
Awesome.
Because
Awesome.
it has to come from the configuration part.
So this is all done like just within VASP.
Just VASP, complete VASP.
Okay. Awesome. Yeah, this is really exciting,
Oh, this one you have to do, because this one you have to do one MD simulation. One
Okay.
MD simulation.
Okay.
And
Okay.
then you get the configuration part from the MD.
Okay. All
Of
right.
course, you can do like typically you take a few hundred steps, right?
Mm-hmm.
Fine. You can do the distribution for each configuration, each snapshot, average it.
Mm-hmm. Okay.
But that error is so small.
Okay. All right.
Yeah.
Thank you so much. Yeah.
Thank you.
Yes, Deepak, come here, ask a question. We have a student ask a question.
Oh, great.
We also work on non-equilibrium thermodynamics.
Uh,
Just go ahead.
Thank you, Dr. Liu. My question is, I want to ask if how would you simulate or calculate transport processes within this framework, or would you need additional understanding or additional equations to model transport processes in materials?
That's a great question. That's natural things I want to do, right? That's natural things I want to do. So you see, I have as my textbook. I have two books come out just printed last year, and we were planning to put in one book. Okay. However, it became too thick. The publisher decided to do two books. Then they asked me for the cover. I said, this cover was designed by Penn State. Then I said, our friend is in the landscape. Then they create this cover for the book. It's just beautiful. So go back to your question. It's really that because this entropy can predict the energy landscape, right? So that means you have two states. Okay, that means you can predict the barrier now. So everything, statistics, everything's barrier is basically it's a kinetics, right? So we believe you actually predict the kinetics. So talk about this case, 300 Kelvin. At 300 Kelvin, you could, on this side, 300 Kelvin is somewhere here, right? This side, you have one phase, and that side have one half phase. But you put in the middle, they're going to, if you decrease pressure, you're going to start to form a new phase, right?
Yeah.
The barrier is here. Now you have the barrier. The barrier is not only energy, it's a Fresnel barrier. Fresnel barrier is very important because it gives you the prefactor too.
Probably, maybe I wanted to ask, like, how would you model a time-dependent process
Okay.
that uses
You can-
a thermodynamic potential, and specifically the tables that you showed in the end that relate various material properties with migration coefficients. So for the calculation of migration properties, do you need additional information, or the derivatives are self-contained?
You need a flux equation, right?
Yes.
Flux equation, okay? So that's what I got in flux equation in 2014. I started getting the flux equation. And then, of course, if that's what I said on Saga, right? You have a Saga flux equation. I found some problem with his equation. I said, that doesn't make sense. Something must be missing, okay? So I wrote a paper. It took me 80 years. Took me 80 years to find that problem. So in 2022, I wrote a big paper. I criticized the Saga equation. I said it was not correct. Okay. And then my colleague, I say, so another paper says Saga is correct. Okay. So I just finished another paper. The case is the flux equation. Okay. How to write a flux equation. Long story short, I just finished another paper. We should be published very soon. Is that go back this very, very fundamental equation. It's a combined law, actually first law even. Okay. The idea is that you need to calculate flux. How do you calculate flux? So my theory is that flux only depends on its conjugative potential. For example, diffusion, there's heat conduction. Heat conduction is only temperature gradient. It's not like any other gradient like Saga has. Okay. Diffusion That's time dependent here. That's time dependent, right? Internal energy change a function of t. T, it can go to gradient of the I got a internal energy, partial internal energy. So you can write flux equation. Okay, now you solve it. So now the question: how to get the kinetic coefficient, right? Okay, that's the barrier. So now this barrier will give us the Li, any transport properties, and then we can predict it. But of course, we have another Corsi phenomena. What does Corsi phenomena mean? It's basically that you have this cross phenomena. And now if you change use entropy, then it becomes very different now. That's another equation. And if you now introduce chemical potential, it becomes even more complex. But it's all from the free energy landscape. Sounds good?
Thank you, sir.
All right.
Thank you.
Thank you. I think give the time. We have to.
Is it Xiaoming? Xiaoming has a question?
Yeah, I
Okay,
have
one
a
more
question.
question.
So
Fine.
very quick. So in your partition function, so you modify the original internal energy and replace it with free energy. I guess it's Helmholtz free energy. So because Helmholtz free energy already included entropy contribution, so now your partition function has the, so you use partition function to calculate the entropy, but your partition function already include the entropy. So
That's
do you double count the entropy?
That's a good question. That's a good Xiaoming, that's a good question. That's actually the question many physicists asked me before when we started. Okay. However, they don't not double counting because this information entropy is between the configurations. Quantum entropy is inside the configuration. Okay. Quantum entropy only affects the probability. So quantum entropy does affect the probability, but the total entropy is summation of them.
Okay.
You can think about one case called if your configuration is a pure quantum state, this one equals 0. Okay, it's because we started with the quantum state configuration, its entropy is not 0. That's why when you go to the quantum statistical mechanics, you don't have that term. You don't have that term because the quantum statistical mechanics starts with the pure quantum configuration. It has no internal degree of freedom, so it doesn't have any entropy from inside. But then you cannot use the classical statistical mechanics. You have to consider the quantum statistical mechanics, which includes the Fermi-Dirac statistics and both Einstein configuration. So it's the same thing actually.
Okay, that's very interesting. So I probably will dig out your paper and read more. It's very interesting. Thank you.
Okay, thank you for your
Thank you.
question. All right.
All right. Thank you so much for the presentation. I think it's very good communication. We'll follow up. Professor, thank you so much. I will see you in Vegas. Well, let's thank our speaker again.
Okay, thank you. Thank you very much. Thanks everybody.
All right.